this work, we explicitly tackle the domain shift problem inherently exists in face anti-spoofing. Nowadays, the increasingly growing number of mobile and computing devices has led to a demand for safer user authentication systems. Face anti-spoofing is a measure towards this direction for biometric user authentication, and in particular face recognition, that tries to prevent spoof attacks. Imagine you have a face recognition system running on your mobile phone which you regularly use to log into different mobile applications, such as online banking to pay your bills, online shopping to purchase things, App Store to install new apps, just to name a few. Every time when you send a login request, the face recognition system on your mobile phone uses your face image captured by the frontal camera to authenticate you as a genuine user of the device. But at the same time, hackers have become more inventive in their attempts to spoof your face in order to fool the authentication system by means of different spoofing attacks, such as printing your face picture on a paper, that is called a print attack, playing a video depicting your face on a display device called the video replay attack, or even wearing a special mask to closely imitate your facial appearance known as the mask attack. Being able to effectively detect such attacks, formerly known as face anti-spoofing, which is a critical problem in computer vision. In this context, the genuine face is called a real or live sample, whereas the attack face is called a spoof. In this work, we are interested in developing a vision-based face anti-spoofing system. In practice, face anti-spoofing systems often suffer from inherent domain shift problem, which occurs when the system is trained on one dataset called the source domain and tested on an unseen dataset called the target domain. The main reason for the domain shift is the feature distribution dissimilarity between the source and the target domains caused by several dataset specific cues, such as differences in the environmental conditions like illumination, background, or differences in spoofing mediums like printers, display screens, or even differences in the quality of video capturing devices, for example, different mobile phones, different tablets, etc. Thus, a model learns to differentiate between live and spoof samples based on these data-dependent cues, fails to correctly classify samples from unknown dataset having different set of cues. The research community addresses this problem following two different setups. In the first one is called the domain adaptation setup, where the system have access to the unlabeled training examples of the target domain. Where in the second setup, the system doesn't have any access to the target domain, called the domain generalization setup. In this work, we address the domain shift problem in face anti-spoofing under the domain generalization setup. Domain generalization seems more practical in a sense that if you want to deploy your face anti-spoofing system in a new place, in most cases you might not have the privilege to have access to the unlabeled samples from the new target domain, as collecting data is always time-consuming and an expensive process. Ideally, what we want is to have a system which could generalize well on an unseen dataset without having any access to it. Now let's have a look at the traditional approaches to face anti-spoofing. They rely on handcrafted features like LBP, HOG, and SURF to detect differences in textures between the live and spoof face images, or heuristics like eye blink, lip motion, and visual rhythms to identify regularities that are absent from the spoof attacks. However, these methods are either not applicable to all possible spoof attacks, that is the print, replay, and mask attacks, or they fail to generalize to different datasets, since the learned features specialize to the trained textures, which largely vary between datasets due to factors like different backgrounds, lighting conditions, camera resolutions, spoof materials, etc. Despite the improved performance of modern deep learning based approaches, they fail to address the domain shift problem in face anti-spoofing. These approaches can be categorized as follows. Works which don't explicitly address domainship problem, works which address domainship under the domain adaptation setup, and works which address domainship following a domain generalization setup. We also follow a deep learning approach to solve face anti-spoofing under a domain generalization setup. We found that Shao et al. Is the only work which addresses domainship problem following a domain generalization setup where they consider each face anti-spoofing dataset as one domain. However, we noticed some limitations in their work which are as follows. The performance of their method heavily relies on an auxiliary depth supervision which is expensive and time consuming. To generate face depth map supervision, one needs to fit a 3D face model for each video frame, which is computationally expensive process. In addition, they follow an expensive multi-stage training strategy in which they first train n CNN feature extractors to learn domain-specific features for live and spoof examples, where n is the number of source domains. Then they train a multi-adversarial deep network to learn domain agnostic representation. Our proposed solution by design addresses these limitations of Shao et al.'s work, that is, it uses only labeled supervision and doesn't rely on expensive depth supervision. It follows a single stage training and shows state-of-the-art face anti-spoofing results. The main goal of this work is to generate domain agnostic feature representation using the source domain samples that would generalize to the unseen target domain samples, so that each sample, regardless of its domain origin, can effectively be classified as live or spoof. To this end, we propose the use of class conditional domain discriminator modules coupled with a gradient reversal layer. At the core of our proposed deep learning framework, we have the image-based network which follows an image level training. It consists of a ResNet backbone which is trained to minimize the face anti-spoofing classification loss, while at the same time it competes against a class conditional domain discriminator to maximize the domain classification loss of live and spoof samples respectively. During the training, the ResNet backbone gradually learns the shared and discriminative feature representations. The class conditional domain discriminator takes as input the feature representations generated from the ResNet backbone and tries to classify from which source domain each sample comes, conditioned on the class it belongs, that is live or spoof. The gradient reversal layer acts as an identity transform during the forward propagation, but multiplies the gradient by a certain negative constant during the backward propagation, essentially reversing the objective of its subsequent layers, in this case the ResNet backbone. This practically means that the backbone network is now tasked with an additional objective of generating live and spoof feature representations that are indistinguishable across domains. In practice, the domain discriminator layer splits the SGD mini batch into live and spoof batches and pass them as inputs to the live and spoof heads respectively. The live and spoof heads output the domain classification scores for each live and spoof examples. By learning features indistinguishable across multiple source domains, our model can learn anti-spoofing representation which generalizes well on unseen target domains. The video-based network is a pretty straightforward extension of the image-based network. To learn temporal domain invariant features, we train an LSTM in parallel with the image-based network. Our video-based network allows to learn temporal domain agnostic features. Now we can have a look at the experimental settings. We consider a face anti-spoofing dataset to be one domain. We use the following 4 face anti-spoofing datasets for training and evaluation: Kasia MFSD, MSU MFSD, OLU NPU, IDIP replay attack. We use half total error rate and area under curve as 2 evaluation metrics in this work. The domain generalization setup used in this work is crucial to fully understand the experimental results reported in this work. We randomly select 3 datasets as the source domains and remaining unseen one as the target domain. Thus, we have 4 domain generalization datasets. First, O and C and I arrow M. Second, O and M and I arrow C. Third, O and C and M arrow I. And the fourth one is I and C and M arrow O. For example, the first dataset O and C and I arrow M denotes the domain generalization setup where the model is trained on 3 source domains OLU NPU, Kasia MFSD and replay attack and tested on the unseen target domain MSU MFSD. Now we compare our proposed method against state-of-the-art face anti-spoofing methods. The methods denoted with asterisk symbols explicitly address domain shift in face anti-spoofing following a domain generalization setup, whereas other approaches don't explicitly address domain shift problem in face anti-spoofing. Note that our method outperforms the existing face anti-spoofing approaches on the first domain generalization setup, that is I and C and M arrow O. We notice significant improvements both in HTR and AUC. Similarly, the proposed approach shows consistent improvements on other 3 domain generalization datasets. Our method achieves state-of-the-art performance without using any expensive depth supervision or multi-stage training. We generate some t-SNE plot to visualize the learned feature embeddings of the ResNet baseline and our proposed model. We use a color coding in which the source domain live and spoof samples are denoted with different shades of green and red colors respectively, whereas the target domain samples are denoted with different shades of blue color, where the darker shade of blue denotes live samples and the lighter shades denote the spoof samples. The ResNet learned representation shows relatively weaker generalization ability on the target domain as shown in t-SNE plot A. The live, print and replay attack features from multiple source domains are far apart in the feature space, as in plot A. In contrast, our model learns more discriminative features for live and spoof images as shown in t-SNE plot B. What is more interesting is that the representation learned by our model aligns well with the unseen target domain's live and spoof features, as can be seen by activating the target domain visualization in t-SNE plot C. In other words, our model learns to minimize the inter-domain distances between live and spoof features as shown in plot B and C. In this slide, we'd like to share some interesting observations of the class activation maps. We randomly selected some live and spoof samples and visualized their corresponding class activation map. For some instances, we found that the network gives more importance to the facial regions for detecting a live class. For print attacks, the network pays more attention to the surface of the paper. For video replay attacks, the network bases its decision on strong features like a hand in the background or a tablet screen. Finally, the key contributions of this work are as follows. We propose a novel class conditional domain discriminator module coupled with a gradient reversal layer promotes learning of spatial domain agnostic features. We integrate an LSTM to our proposed framework to learn temporal domain agnostic features as complementary information. Our proposed method achieves state-of-the-art results on the 4 challenging domain generalization dataset. We provide an in-depth visual analysis of the feature embedding. For more information, please check out our paper Thank you for your time.